Welcome to another video. We are starting section 11.3 where we cover the integral test. This is the first of a set of techniques that we can actually use for a variety of different series and not just one specific flavor of series. And the motivation for working with these actually comes from some examples we've already worked with so far. So we're going to consider, hang on, my pen didn't want to turn on. There we go. Okay. Consider the set of series, right? So it's a generic kind of series, starting at n equals 1, where the terms of the series look like 1 over n to the p for some real number p. So this could be an integer value, it could be irrational, it could be negative, it could be positive. 0, though, is not an interesting one because that ends up just being a sum of 1 forever, which we know is not interesting. We call this a p-series. It's fitting, since that's what defines this kind of series. And so our question is, for what values of p does this converge? So my claim here is that not every value of p is going to give us a series that converges, but some of them will. So in order to get some intuition about this, we're going to play with two different examples. And the way that we visualize them is going to motivate our definition for the integral test. But before we get into that, let's talk about a preliminary case, right? Case 1, which is the p equals 1 case. And that gives us the series with terms 1 over n, which we know is the harmonic series. And in a previous video, we've talked about this series, which we know diverges. Okay, so we have our first sample point, which is if you plug in 1 for p, this series diverges. So that suggests that if we look at either side of 1, maybe something interesting will happen. So let's look at case 2. And I'm going to pick deliberately p equal to 2. So we're going to consider the series of the sum of the inverse of squares. Okay, so if we want to visualize this, the inverse of squares misleadingly will make you think that we want to look at actual squares, but we're actually going to look at rectangles here. So each rectangle that I'm going to draw is going to have the same width, but different height. And the height is going to correspond exactly to the term of the series. So the first one is going to be 1 unit by 1 unit. The next one is going to be 1 unit wide and 1/4 unit tall. So it might look like this. I'm not being very exact here, even though I have the graphing paper, but you're welcome to be more precise than I am when you're drawing this. So that has an area of 1/4. Next one is going to represent the next term in the series, which is going to be 1/9. Notice that they're getting smaller rather quickly. Smaller in the sense that they're shorter rectangles. Okay. 1/16. At this point, I'm going to stop being able to draw these because I'm not, my hand isn't that precise. 1/25. So if you can imagine that we'd be going out forever to the right, and the sum of those areas represents the sum of this series. Now, I want to illustrate that if I take the upper right corners, and I think of the function going through those corners, right? So it's going to go through, if this is the origin, it's going to go through 1, 1, 1, comma 1/2. Sorry, 1 comma 1 quarter. I'm sorry. This is representing then y equals 1 over x squared in the first quadrant, right? So really, if we think about this, what we're saying is that the terms of the sequence are the floor function applied to this real valued function, 1 over x squared. And in particular, because of that, the area underneath, specifically, starting here, this area, which whatever color you want to call that, I'm going to call it red. Maybe magenta or maroon is more accurate. But that area, then, we can see, so we reasonably have a geometric sense that the sum, the series, over n squared, has to be less than the integral from 1 to infinity of 1 over x squared dx. Why? Because if we break it up into every piece, right, this integral is going to give us a larger corresponding area than the rectangle underneath, right? So here's the payoff, though. This inequality is true. Okay, I claim that it is. And we know, and I'm saying this loosely in the sense that we know in the sense that by working with improper integrals, we have seen this particular improper integral before, and we know that this converges, okay, to 1. So it's a finite value, which means our series is bounded above by a finite value, and it suggests that the series converges as well. That's crazy. In fact, and this is, I think sometimes called the Basel problem. It was known to Euler, but this series converges to pi squared over 6. Why? It's not immediately clear to us right now. There's a fantastic video actually by 3 blue, 1 brown. Or is it 3 brown, 1 blue? I don't remember. But I'll link it in the assignment, in the section page, so you can see it for yourself. We'll also see this again when we talk about power series representations of functions. But for right now, the actual value of the series doesn't matter. We just know it converges. Okay, let's talk about case 3. And in this case, we're going to take, p equal to 1/2. So that corresponds to the series consisting of the terms 1 over square root of n. Okay, so let's visualize this again. Again, I want the widths of my rectangles to be 1, each one, and the height to be the corresponding value of each term. So the first one will be 1 by 1, or if you want to think about it as 1 over the square root of 1. The next one's going to be 1 over the square root of 2, something like this. Again, I'm not being very accurate, but roughly that's what we're talking about. 1 over the square root of 3, 1 over the square root of 4. That one is actually 1/2, right? One over the square root of 5, and so on. Okay, if we could imagine that we keep going out further and further, then the sum of all these areas would be equal to the sum of the series. If it's finite, it converges. If it's not finite, it diverges. And now I want to bring your attention to another curve that I'm going to represent with red here. And instead, it's going to go through the top left corners of these rectangles. So it looks something like this. Okay, one thing to note is that regardless of what you know about this curve, right? Which, by the way, I'm going to write as y over 1 over the square root of x. So this real valued function is giving us this red curve. And the corresponding integral, improper integral, of this function is represented by this red area, which is an underestimate of the sum. So we can see, similarly to our previous case, this red area, right, is going to be less than, actually, the sum of the series. Right? Geometrically, we have a good grasp of what that means, and we could make this precise in the limit sense by taking each rectangle, right, and seeing that the corresponding areas in each subinterval must also be satisfying this inequality, and this trend continues out as we go further and further out into the tail of the tail of the series and the tail of the improper integral. Square root of x dx. Okay. And here's the payoff, right? This integral diverges. Okay, we did see this briefly when we talked about improper integrals. It was a pattern that was kind of interesting and it came up. And this is really where we get to use it. So I said then that it's interesting and you want to keep a lookout for those sort of patterns. This is where that pattern is actually something that's going to help us. If this diverges, right, that means this represents something that's infinite. And so this sum must diverge. It does not settle on any number. It is also infinite. Okay, so this technique is going to generalize to what we're going to call the integral test, okay? And the integral test is what's going to help us make precise our conjecture about p-series, which is 1, if p is greater than 1, then the p-series converges. 2, if p is less than or equal to 1, then the p-series diverges. And it's the power of the integral test that helps us see that this must be true. So in the next video, we'll actually go over the integral test and sort of see why it has to be true. We're going to take a very loose justification as we see with pictures like we did with these two specific examples that we highlighted. And then we'll get to apply the integral test to more exciting and exotic series.